Good morning and good afternoon, everybody. Welcome to today's webcast, an introduction to MemSQL for developers. My name is Jennifer, and I'll be your moderator today. Before we begin, there are just a few housekeeping items I'd like to review. This webcast is being recorded, and you are currently in a listen-only mode. You may submit any questions you have throughout the webcast via the Q&A or chat function in the lower right corner of your console. You can also follow us on Twitter @MemSQL or live tweet us during the webcast using hashtag MemSQLWebcast. We will address everyone's questions towards the end of today's presentation. After the webcast, you will receive a follow-up email with a link to the recording and slides. If you wish to contact us, please send us an email to team@memsql.com. So let's begin today's event. In today's technical webcast, we will cover off on topics on why companies use MemSQL. We'll share technical architecture that delivers a scalable SQL database, key capabilities that distinguish MemSQL from other data stores like NoSQL, and how MemSQL works with ingest tools like Kafka and Spark. With that said, I'd like to introduce today's speaker, Neil Delkey. Neil is a senior solutions engineer with MemSQL. He joined MemSQL in late 2013, where he began working on building and monitoring management tools for MemSQL and MemSQL's users. Nowadays, he works directly with users to understand how to leverage MemSQL advantages to their full potential. Thanks for joining us, Neil. You have the floor.
Thanks, Jen. So hello, everybody. I'm Neil. I'm an engineer, as you mentioned. I'm going to cover some high-level concepts with MemSQL and how to leverage it, as well as the architecture. I just want to make sure here that as I change the slide, you got the new slide. No, it looks like that's the last one. So give me 1 second here. Okay, there we go. You got the new one? Cool. Okay, so these are the topics I plan to cover today. So we're going to go through, we just do the introductions. I'll go over the high-level architecture. We'll talk about row store and column store, how data is just distributed in MemSQL, how that affects local and distributed joins, MemSQL code generation, MVCC, which is multi-version concurrency control, loading data into MemSQL, and if time allows, we'll cover some of the topics under ACID in MemSQL. So let's just get started here. So in one slide, this is MemSQL. So we're a database, distributed, ACID compliant. I'm not going to read everything here, but if you guys were to take a screenshot out of the slide to share with your coworkers, this would be a good place to start. In the context of this discussion today, these are all of the topics I plan to cover within MemSQL. So we'll talk about how we're distributed, how it's a database. We'll talk about anti-SQL, MySQL protocol, how we handle large levels of concurrency, how we do fast queries, reduce query latency, so on and so forth. And then, of course, ACID compliance we'll cover if we have enough time. So to give you kind of an overview of where MemSQL sits in the world, this is kind of a good idea. So we are a database. We handle large volumes of live and historical data, and what that means I'll cover in a couple of seconds. But we sit here in this kind of middle tier where we basically will ingest data from sources such as Kafka or Spark, or from historical databases like your Oracles of the world, or Hadoop, or Amazon S3, or a remote file system. There's all sorts of different places that will allow you to load data from, and I'll cover some of those topics later. On the other end of this, we have the access layer. So we're talking your real-time applications. This could be a homegrown application that's leveraging a JDBC or ODBC driver, or a popular BI dashboard like Tableau or Looker and MicroStrategy, and so on and so forth. One of the ways we gain connectivity with these, aside from our partnerships with the great kind of BI vendors, is MemSQL speaks the MySQL protocol. So anytime you guys want to use a tool with MemSQL, if you don't see MemSQL in the drop-down list, you can just select the MySQL driver, and you'll get great connectivity that way. MemSQL is a software-only solution, so we do not package this with any hardware. There's no appliance. We'll run on bare metal virtual machines or containers. All we ask is that you have a modern 64-bit Linux kernel, and you can run this in any cloud, on-premise, wherever you really want to run it. I run it on my laptop from time to time in Docker, and then obviously we have our customers running it in things like AWS or massive on-site data centers. So just in the interest of time, let's just jump right into it. So the high-level architecture, MemSQL is not magic. It's a database. So basically what it boils down to, it's a MemSQL Linux daemon. And we can see that here is the MemSQL D. But in general, nobody runs one MemSQL instance. They run multiple MemSQL instances. So you can kind of see here, MemSQL is a distributed system. What does that mean in the context of MemSQL? Well, we have two tiers of machines inside of our architecture. We have the aggregators, which aggregate and provide a connection point to the cluster, and as well as kind of abstract away any type of partitioning logic that you'd have to think about any other way. Leaves are where we actually store your data and where we actually process your data. So there you can see here the leaves are holding the partitions. Let's just walk through a quick example of what that looks like. So it could be, a command line client. It could be, SQL Workbench or all sorts of different tools. We're going to connect to the aggregator with the client. So that could also be, any type of JDBC, ODBC, MySQL connector. And we're going to run this query over here, create database foo. So what happens after we run that create database foo? If we logged in with our client directly into the leaves and we ran the show databases command, what we actually do when you create your database through the aggregator is we're going to go ahead and create a single database per partition on each of the leaves, or per core on each of the leaves, and those would represent a partition. So in this example here, we've got foo1, foo5, foo7, foo9, and of course, if we connected to this other leaf, we'd see things like foo0, foo2, foo4, et cetera, et cetera. Now, we leverage MPP, or massively parallel processing, with this architecture in this particular method. So say I connected with my database clients to the aggregator, and I issued this query, select average price from orders. What would happen is the aggregator and the query optimizer and query processor would take that and interpret it. And so in this particular example, what it does is it goes and it says, okay, on leaf 1, using MemSQL demo 9, or whatever partition you want, let's get the count and the sum for that individual partition. That's going to execute fully in parallel, so that these partitions are created one per core. So by default, we'll have one core acting on each partition at any given time. Then the results of each of these kind of micro queries will be zipped up, sent back to the aggregator. The aggregator will do the final averaging of the prices. Now, obviously, in the modern ecosystem, your system needs to scale. So here's an example of how you would add more nodes into a MemSQL cluster. So basically what we would do is we'd spin up 2 more, instances. This could be VMs or anything, as I was mentioning earlier. We'll install that MemSQL D software. And then in the aggregator, we say add leaf, and then we give it the host name and the port that we want to add. Then we'll run this command, rebalance partitions. We'll take some of the partitions from the leaf over here or this leaf over here, and we'll shuffle them around to the next one, and so on and so forth with the next leaf. The kind of same can be done in inverse here, where you want to remove leaves. Say it's like you have a seasonal business, you want to scale it up, scale it down. If the seasons pass, you can do that. So that's just kind of an example of how easy it is to do. We can also scale the aggregators. So, this is just an example. Basically, with the aggregators are stateless, so you don't actually even have to run that command. You just spin it up, and in this memsql.cnf file, you tell that aggregator where your master aggregator is going to live. So I'm going to jump right into row store and column store. I'm assuming that some people on the phone here are somewhat familiar with one or both of these concepts. But maybe not so much in a system where you can really leverage both. And for those who aren't, I'm going to kind of cover exactly where you'd use these types of tools. So MemSQL has the in-memory row store and the disk-based column store. The in-memory row store is very similar to your kind of traditional Oracle workloads, or now your more modern like Cassandra NoSQL workloads. So that's a lot of OLTP, single record inserts, random seeks. So this would, kind of think of a customer 360 use case where you need to quickly extract all of the information about a single customer, or an Internet of Things, or kind of a telemetry use case where you're constantly streaming in millions of records about the health of, individual storage arrays in your data center or something like that. It's a great fit for an in-memory row store. The disk-based column store is for OLAP workloads. So this is more of your traditional BI type of stuff. Things that would, historically be covered by like a Vertica. That is something that has big loads, kind of batches, not really a real-time type of use case. It does fast scans and aggregation. You're rarely updating it, and you delete records in bulk. So, neither one of these things is particularly novel. They've been around for a while, but it is quite interesting to have a system that has both of these utilities within one. And MemSQL allows you to join these two together in a single query. So how does that get done? We'll cover it right here. So all of this is determined at a table level. So let's just say, for example, we had a row store table. Row store tables are going to store all of their indexes and data in RAM. So, all of your individual partition data is going to be stored in RAM and every single bit of information about it. Whereas column store tables, and you can see here, this is a simple example of creating a row store table. So it's very similar to, like I mentioned earlier, creating tables in MySQL. You just, your simple create table statement, and you got a primary key. Nothing seems out of the ordinary here. That's because this is the standard vanilla table that you can create in MemSQL. So this is going to be all in memory. Now we also have the column store stuff. The column store stuff is beneficial in so much as you kind of can use your resources in a little bit of a different way. So the column store stores all of your indexes and metadata in RAM. So that would be, the locations of your individual column segments, what's the min, the max, the average value of all of the values within an individual column segment, et cetera, et cetera. But all of the actual column segments themselves, the data, is going to be stored compressed on disk. So, I think you guys can probably kind of see from here that you kind of get the best of both worlds from the old traditional view of the database ecosystem, where you can do your high velocity OLTP type of workload, but also have all your OLAP same system and actually kind of compare data as it's happening in the moment to historical data as it's happened over the last 3 years. See, creating a column store table here, it looks very similar to creating a row store table. The only difference is when you define your key, if you see back here, we had the primary key. Here we say key using clustered column store, and that's going to go ahead and create a column store format table. It's just that easy. Then, as you can see again, this is the orders history table. You can just join these two tables together. There's nothing crazy about it. So data distribution in MemSQL. So we'll go back to that example I was showing you earlier with the simple create table orders, primary key, order key. So, and then we've got this new key here, shard key, so order key and cust key. The shard key is the key that we're going to use to determine where that piece of data is actually going to live within your cluster. Like which partition is that thing going to go live on? So let's take this kind of simple example here. Insert into orders, values, blah, 1, 2, 3, 4, 5. And then we can kind of watch as we pass through here. So insert into orders. Okay, we've got the values, and order key and cust key are our two first ones here. That's what our shard key is. So we're going to take those two values. We'll concatenate them. It's not necessarily with a pipe, but for the example here, I think this is easy enough to understand. Concatenate them, pass them through a hash function, modulo that by the number of partitions, and that's going to give us a partition for which that piece of data is going to go live on. What that kind of looks in the broader spectrum here is, okay, insert into orders, I got my values, I take my shard key, I get my hash, I modulo the number of partitions, and I determine which partition it's going to go live on. So you can kind of see from the insert all the way to where that data goes and finds a home is over here on this little kind of orange partition. Why that's important, aside from eliminating skew, for example, and having more data on one node than on all the other nodes, is for local and distributed joins. So MemSQL allows full distributed joins. There's no lockouts, which is very talk about how to do it. So let's say we've got this simple example here. I've got table A and I've got table B. And there's nothing super crazy going on in either of those tables. But what I want to do here is I want to select star from A, join B, where A.color equals B.color. What's going to happen when I run this query is going to be entirely dependent on how I choose to shard the actual data. So let's say, for example, I shard that data on color. Well, then we'll get this nice kind of picture here, because as we showed on this, anytime we shard on the same value, so we pass in the color, say black here, and we hash the color black and modulo the number of partitions, we know that we're going to get the same exact location for that actual piece of data. So even if it's in table A or if it's in table B, when we go to join those two pieces of data, they're going to be nice and local, and we won't have to do any kind of network traffic. Now, if I take a step back here and say, I didn't shard these guys on color. Say I sharded one on cust key and I sharded the other one on part key. Well, then you can get a query that looks a little bit something like this. And obviously, this is a lot of network traffic. So this is not going to kill you in every scenario, but it is something that you need to be cognizant of when designing a schema in MemSQL, because the implications on your query execution are quite large. If you're doing this, say, with a 1 billion row table against a 100,000 row table, you can probably infer that that's not going to kill you. But if you take 10 billion rows and join it to 10 billion rows, and your query plan looks something like this, you can expect to see quite a bit of network traffic, and it might slow you down. Now, the world is not perfect, and then you can't always shard things on like keys. And so we understand that. And so we also have a helper table that we call the reference table. The reference table probably could be better called a dimension table, as that's the way that I like to think about it. So a reference table keeps a copy of that entire table on every node in the cluster. An example I like to use for this one is, say, you're the USPS, and the USPS has a fax table of deliveries, and it's, call it 10 billion rows wide for the last 4 years or something like that. That's a table that's large enough that you want it to be distributed and sharded across the cluster. You don't want to have that entire table on any one node. But say, in the interest of saving resources in terms of disk space or disk utilization, then you may want to, go with the column store, or you may want to, not store all of the individual information about each city on each delivery. So instead of keeping the city information, you'll keep the actual, just the zip code, and then you'll look it up against the zip code table. The zip code table will only have, up to what, 100,000 records. And so 100,000 records is actually quite small, and that would make a great candidate for a reference table, because if we do a join between that giant fact 10 billion row delivery table against a local 10,000 row zip code table, then we don't have to do any network traffic at all. And in fact, every join against that table will be local. Code generation. So MemSQL is a pretty modern database, and we do make quite extensive use of code generation. And what does that mean for you? Let's kind of talk that out. So do this is because it allows us to kind of optimize for low-level situations that will get you the biggest performance boost whenever we can. We parameterize our code gen, and our code gen is also deterministic, so you should get the same plan for the same query every single time. And it's quite low latency query compilation, so we actually rewrote our compiler from scratch. So let's just kind of walk through what that looks like. So say I want to select star from table 1 where ID equals 1, 2, 3, 4 and name like Jingleheimer. So the initial time that you execute this query, you're going to come through and you're going to hit a parse phase. The parse variable. So if we look over here, this is what a parameterized query would look like. So we've got ID equals, and we got the caret where Jingleheimer was. Once we've got this kind of parameterized plan, we pass through the code generation phase. So the code generation phase takes SQL, generates MemSQL bytecode. MemSQL bytecode is passed into LLVM. LLVM generates. We store that in the plan cache. You can think of the plan cache as a key value store of the queries that you run. So this right here would be the key, and the actual machine code would be the value. So now, any subsequent time you come in and run that query, we can skip any type of interpretation steps and get straight to our optimized code. And so we hit this parse phase. The parse phase would go ahead and parameterize. We'd skip through that code gen phase right to execution. MVCC. So another common problem that people come to me with when they're looking for a new solution is more and more people want access to this data than ever before. It used to just be the executive levels or maybe a handful of business analysts and so on and so forth. But now you've got every person in sales that wants access. You've got every person in marketing. And how do we basically open up that system to more and more people without performance degradations? So MemSQL uses MVCC. Some of you guys may be familiar with it. I'm going to walk through exactly how it works. But basically, these are the kind of common concepts here. So I think the most important one is that their reads are never blocked. And we only do row-level locking for writes. So this enables your business to constantly be using the data, even if people are manipulating it. A lot of times, people will take locks on reads, and so that can kind of slow down your business. So let's kind of walk through what that looks like. So let's say we're creating our first version of a row. We've got row version V0. Okay, so we go ahead and we write that. Now, nobody accesses it. Here we come, and we're going to update that row again. So we've got version 1 coming in. Now, once version 1 is finished writing, the MVCC manager is going to go ahead and garbage collect that initial version of the row. Now we've got a reader. Here comes somebody who says, okay, now we've written that row, it's valuable data, I want to come in and see what it looks like. As that person is reading it, another writer comes in to update that row. Now, the second version of the row has completed writing, but the read for version 1 has not completed reading. So we still hold on to that original, or that V1 of the row. Okay, V1 is still not done reading, but we have 3 other readers who have come in and want to read V2. Okay, that's totally normal, right? So basically, as you can see here, nobody is ever being blocked from reading from the system or having their query interrupted in the middle. Now to add some more kind of complexity to the mix, here comes another writer. And so, we've got V3 writing here. And here comes another one, V4. So as I mentioned earlier, we take locks on write, not on read. So in this particular scenario, you can see when that lock until version 3 of the row is completed writing. Now, once that initial query finishes, we go ahead and we garbage collect that one as well. And you can kind of infer how that goes, from there on, and how the weighting and all that kind of stuff works. And so MemSQL does have all the normal utilities of a database, like load data local, or inserts and all the kind of stuff that is pretty common into getting data into a database. But one thing that I find very cool is MemSQL pipelines and the kind of things that you can do with it. And I'm going to kind of just go through this quickly because I believe we have I got 3 minutes left roughly. Yeah. So MemSQL is designed for stream ingestion, batch loading. It's fully parallelized. You can do whatever type of transformation you want to do on it. We have exactly once transactional consistency, which is pretty cool. And I promise I'll cover exactly how we do that very shortly here. So let's just take a quick look at an example of what creating a pipeline in MemSQL looks like. So I've got this statement here. So create pipeline. This is very similar to create table, create database, give it a name. So create pipeline, Twitter pipeline in this particular example, as load data Kafka. So right here, this is where I'm telling my pipeline that the source I want to pull from is a Kafka cluster. And then I pass in, I got a host name, I've got the port for my broker, whoops, and I've got the topic that I want to ingest from. Now, I've basically told the pipeline where to find the data. Now I want to tell it what to do with the data. So I want to load it into table tweets. And then I can also pass, and this is one of the really powerful things here. I can pass this third argument or fourth argument, depending on how you count it, and that is called with transform. Now this right here will be a path to an executable. This executable can be written in any language. So I think the most popular ones that I see are probably Python and Golang. Python because of its ease of writing and debugging. And then Golang is also quite popular because it statically compiles and it's quite portable. So we basically pass where this transform is, and we can pass any type of arguments we want to. Say these were different. We want to, filter out this stream differently from another one, but still leverage the same executable. In this transform, all you have to do is read from standard in and then write to standard out. For the sake of time here, I'm not going to cover it. And then it'll go ahead and persist it into MemSQL. After we start the pipeline here, we'll start pipeline. Now, just to give you an idea of what that sequence looks like, and then I'll pause and pass back to Jen. But so basically what we have here is we've got MemSQL on one end, we've got our data source on this end. So the example I'm using is Kafka, but it can be all sorts of different data sources like your HDFS cluster, an S3 cluster, NFS. And so MemSQL is going to pull for changes on those source systems. Now, once MemSQL detects a change on the source system, we're going to pull the data into our memory space. So that's kind of what this orange represents, which basically says that piece of data now has landed in something that MemSQL is managing, and you can apply your transforms to it, but this data is not yet committed to the database. So obviously, if this failed, we would want to retry, right? And so now, once you've performed whatever type of transform you want, we will go ahead and persist that to MemSQL in a transaction and in parallel. Each of these individual leaves is going to pull from the Kafka broker itself, run its executable code, so you can do it. So you can get a fully parallelized ingest from one of these remote sources. Then we also make sure that we get the exactly one semantic, because we actually store the data directly next to the metadata around what offsets we consumed. And so we'll constantly be checking in with the Kafka broker to see, are we behind, or can we wait, and so on and so forth. And so with that, I'm going to pass it back to Jen and see if we have any questions.
Great, thank you. So let's answer a few questions from the audience. Just a reminder, you may submit questions through the Q&A function located in the lower right side of your console, or tweet us using hashtag MemSQLWebcast. So let's get started. First question, what advantages does MemSQL have over an open source database like Apache Ignite?
So Apache Ignite, besides being kind of handled within the Apache space, is not actually a kind of, in my opinion, a true database. It has a lot of kind of issues with it. So Apache Ignite has had SQL appended to it as a kind of secondary appendage. So it was not originally built for it. It's really more of an in-memory grid, so to speak. So a couple of other things. Basically, the smaller surface area kind of reduces all of the complex things you can do with Apache Ignite. So you don't have like stored procedures or any kind of traditional like OLAP database features. There's also a poor transactional consistency story. So Apache Ignite is actually only ACID compliant when it's a key value database. And I know I didn't have enough time to get into how MemSQL handles ACID in this particular demonstration, but we do it better than them, and we can do it with actual structured data. It's really a cache. It's not somewhere you want to run your business from, and it's got no option for a column store, which is something that we saw our customers see kind of a large value in being able to switch back and forth between the row store and the column store within a single system, and do different types of queries and so on and so forth.
Great, thank you. One other question. What are some of your larger concurrent user deployments in terms of number of users, and what type of application is it supporting?
Sure. So I will use just an example. So one of our financial institution customers, they've got a lot of high net worth clients, and they run their entire portfolio analysis platform on top of MemSQL. Now that organization, these people have to pay millions of more money than I'll ever see to be a member of this particular portfolio analysis tool. And so most people don't tend to look at the markets until something's going wrong or something's going great. And so what that means is that everybody hits it at the same time. So for this particular financial user, we do need to serve 2,000 concurrent queries within 1 second to meet our SLAs. And so I think that kind of gives a good example of the types of data, or the types of concurrency. That's on a large terabyte scale of data as well. So I think that probably gives a good viewpoint of exactly what can be handled with MemSQL.
Thank you, Neil. One last question. How do you handle crash consistency?
So that's kind of in the ACID space, and I think that question leads to a lot more questions. I'd probably prefer if we took that one offline, just because it's not
great.
Not something I can answer.
Yeah, we can definitely follow up. One more question. How much time does MemSQL take for an aggregate query from a table of 1 billion rows?
So this always depends. We just recently published a benchmark where we're doing 1 trillion rows in a second. But that may not be a data set that's representative of the work that you guys are doing in your businesses. So my general thing is just try it out if you want to see what we can do. So we do have enterprise trials, but we also have a developer edition. So you can just, spin it up on your Docker instance on your laptop and play around with it. Yeah, I mean, we do billion row queries in milliseconds all the time. But if your table has 7,000 columns, that may not be the case. So it's kind of a, as always with engineering, the answer, it depends. But that type of scale is not scary. And I think we can also probably follow up with some documentation on that trillion row benchmark as well.
Awesome. That is unfortunately all the time we have for questions today. So thank you guys for joining us. I want to thank Neil and each of you guys for attending. As a reminder, we will be sending you a follow-up email with a link to today's recording and slides. If you have any questions in the future, you can send us an email to team@memsql.com. And we invite you to check out additional resources from MemSQL at memsql.com/resources or request a personalized demo at memsql.com/demo. Again, thank you guys for participating and have a great remainder of the day.